Hi, welcome back. So we'll continue our discussion on model complexity. In the previous video, we created an experiment. We created a synthetic data and we tried to build a very simple mean model to start with and figured out how well the mean model is able to capture the true underlying relationship between the features and the target variable. In the synthetic data, we only created our own data set. We know the true underlying relationship, but we are experimenting with the data by building models of varying degrees of complexity just to create our own understanding of model complexity by doing. So let's get going. So in this experiment, what we will do, we will create a linear regression model to capture the true underlying, whether it captures the true underlying relationship between our features and the target variable. So linear regression also actually fits a straight line to the data that we give it to that model, but with a little difference. Like the mean model was able to only fit the horizontal lines because we created an expression that is y hat is equal to y mean, meaning the predicted variable y hat, we equated it to y mean, the average of all y's in the data set. So that's why it's always a horizontal line. But a linear regression can fit lines with slopes. So that is the difference. And let's figure out how do we do that. So to achieve a linear regression model, we have to make our equation a little bit more complex. So the equation that we will use is y hat is equal to beta 0 plus beta 1 x. Like in our schools, we always used to study y equal to mx plus c. That is the equation, a slanted line. That is the equation with which we can represent. So here, what is y hat? Y hat is the predicted value of y for a given x, and beta 0 is called the intercept, meaning whenever x is 0, wherever the line cuts the y-axis, that's what we call it as intercept. And that is very important for identifying the best line that fits our data. And beta 1 is the coefficient of the input feature x, and it is the slope of the line. So we have two coefficients, beta 0 and beta 1. Beta 0 is the intercept and beta 1 is represents the slope of the line based on the input features. So when we use linear regression and when we use this expression and try to fit a model, then what happens will be actually the model will try to estimate the best values for beta 0 and beta 1 based on the data set that we are using. So exactly whatever the line that fits very well to the input data that we are providing to this model, that's what it will fit. So let us see how it works, and let us, anyway, before we conduct this experiment, we have to do the initial tasks. That is, we are importing all the important libraries that are needed for us. So in this, we have done that. And then we are creating our synthetic data. So we are creating 100 values of x evenly spaced from 0 to 2 pi. And then we are creating a y hat that is actually sin x plus some random noise. So to create that, we have run this program. Then we are here seeing the last 5 records that have been added to our. So a table has been created by doing and executing this part of the code. Now let us visualize that using our pyplot. So this is how the data is looking. So there is a true underlying relationship that is actually sin x. That's what we know, but we intentionally added a random noise, and that is how the scatter plot looks like. So now let us look at our regression model. How do we build it and analyze it? So fitting a linear regression model, basically our goal is to use the data set to train the model. So we have 100 100 records now with x and the y equal to sin x plus c records, and we have to use the data and train this regression model. And as we told earlier, when we train with our data this regression model, as an output we'll get these two coefficients beta 0 and beta 1, the best line that fits our data. So that is what we'll look for it. So just to write code for this, so for all the algorithms that we want to use as part of this project, we'll be using, as I told you, a framework called scikit-learn. Scikit-learn has a lot of good algorithms across regression, classification, clustering, many algorithms. So we'll be using that. So what we are doing here is that from scikit-learn, we are importing the linear regression library, and we'll be using it. So what we will do first actually in the code, once we imported that, we will assign or initialize one model with our linear regression model. And then what we have to do is that now in our table, we have X and Y values. So, but this regression function requires two inputs, that is feature and target. So let us actually separate from the data the X column and equate it to features, and the Y column to target. That's what we did by those two instructions. And then we are using the fit function of our linear regression, and we provided this features and target. So we gave our data set to the linear regression model and asked it to fit that. So this is the code that we have executed. So when we execute this code, what happens? The linear regression model, that algorithm runs few iterations, and when it optimizes the line with the right intercept and the right slope, actually it stops and provides some output. That is what is the beta 0 and beta 1 values. So let us look at what is the beta 0, beta 1 values. So the values we have printed here. So that is what for this data set that we have provided, the algorithm finally came and stopped at beta 0 and beta 1 with these values as listed here. So now if we plot the values now, so this is our scatter plot with the blue dots there, and the black slanted line is actually, what is that? It is based on our beta 0, beta 1. For every X value in our table, we have substituted those beta 0 and beta 1 to our Y hat equal to beta 0 plus beta 1 X. To that equation, we have substituted beta 0, beta 1 values, and we created a values of Y that this model will actually identify as predicted variable. So that line we have plotted, so it looks like this. So how does this model look like? So we are not really bothered right now about how that algorithm is working and all. We'll talk about that later. But now we basically conducted a simple experiment and ran a linear regression model, and we have figured out how actually the slant happens in this data. So what do you say about this model? Is it representing the true underlying relationship between the input features and the target variable? What do you say? So just to quickly understand how this may be really working, because you may be curious how this algorithm may be working. So this algorithm will have to start, once it runs with the input data, this program, it will have to start with some kind of beta 0, beta 1 values, and take the data and keep on adjusting itself, where the whatever Y that is being calculated, the error between the Y that is already there in our data set that we have given, that is using which we are training the model, and what based on the line that it is predicting or projecting, based on that line what could be the Y, and the difference between these two Y's is taken, and wherever the error is minimum between this actual Y that is there in the table and the projected Y based on this slanted line, wherever the error is minimum, that is where actually the line is telling this is the optimum line to fit this data. That is what is happening. We'll talk about how linear regression models are algorithms work and how do we develop our own. But right now, keep that in mind. So, but let us go back and understand what happened with our model here with linear regression. So, how did this model do? So, the linear model actually fits synthetic data set that we created little better than the mean model, because even just seeing it, we can figure it out. So by allowing the line to have a slope, actually we have permitted more flexibility than the horizontal line of the mean model. That is for sure happened. But also, what is the limitation of the linear regression? Linear, still it is a slanted straight lines, not, it cannot understand the curvy nature of the data. So the curvy relationship, like our sine wave, that is the true underlying relationship, that cannot be easily represented using simple linear regression model. And that's why still this model is not that complex. It is still not able to truly understand the underlying relationship between our input feature and the target variable. So it is still an underfit model. So that is, with that in mind, let's work on the little bit complex models where we can capture the curvy relationship between our input feature and the target variable. So with that in mind, let's say stay tuned for the next video. So till that time, learn and have fun.